Hi, this is Alex from devstories.eu. PyTorch Fundamentals, episode 13 of 18. The most common bug in PyTorch training is not bad data or a wrong architecture. It is forgetting to clear out your old math, causing your network to spiral out of control. Today, we cover optimizers and gradient descent, which handles exactly how your model learns from its mistakes. Your model makes a prediction, and you calculate the loss to see how far off it was. Now you need to adjust the internal weights of the neural network to make the next prediction slightly more accurate. This process of nudging the parameters to minimize the loss is called optimization. The optimizer is the specific algorithm that governs how those weights change. To configure an optimizer, you must give it two things. First, you pass it an iterable containing the model parameters you want it to adjust. Second, you provide a learning rate. The learning rate is a fundamental hyperparameter that controls the magnitude of the changes applied to the weights. If the learning rate is too small, the optimizer takes microscopic steps, making training painfully slow. If the learning rate is too large, the optimizer overshoots the optimal values, leading to wild, unpredictable behavior. A standard algorithm for this task is stochastic gradient descent, or SGD. It evaluates the slope of your loss function and takes a step in the opposite direction to descend toward the lowest possible error. Once you initialize your SGD optimizer with your parameters and learning rate, the actual updates happen in a strict three-step sequence. Step 1 is clearing the slate. You call the zero-grad command on the optimizer. This is where that common bug lives. PyTorch accumulates gradients by default. When it calculates new gradients, it does not overwrite the old ones. It simply adds the new numbers to the existing totals. If you skip this zero-grad step, your current batch math is corrupted by the leftover numbers from the previous batch. Always zero the gradients before doing anything else. Step 2 is calculating the new gradients. You take your calculated loss value and call the backward command on it. This triggers back propagation. PyTorch travels backwards through your network architecture. It calculates the derivative of the loss with respect to every single parameter. Essentially, it figures out exactly how much each individual weight contributed to the overall error. These calculated gradients are stored directly inside the parameter objects. Step 3 is applying the fix. You call the step command on the optimizer. The optimizer looks at the gradients stored in each parameter during the backward pass. It multiplies those gradients by the learning rate to figure out the exact size of the adjustment and then updates the actual weights in memory. This cycle repeats for every batch. Zero the gradients, calculate the backward loss, step the optimizer. The critical detail to remember is that the optimizer only updates the parameters it was explicitly given during setup. If you need to freeze a layer in your network, you simply exclude its parameters when you initialize the optimizer, and those weights will remain permanently fixed. By the way, if you want to support the show, you can search for DevStories EU on Patreon. Thanks for listening. Take care, everyone.